In this presentation, we're going to look at dependent samples and the difference between dependent samples and independent means. In dependent sampling, you have a same set of sources or related sources used to obtain data representing maybe two populations. It may be a single population with two variables. One way to picture this is that you have a single sample or two related samples that provide you with the two variables that you're studying. With independent sampling, you have two unrelated sets of sources, so one from each population. And so one way to picture this is that you have your two samples, and each of those samples provides you with a variable. And there's no relationship between those two samples. An example of each of these would be if you were testing. Let's say that we give a pre-test and a post-test to students in this class. A pre-test, maybe a test similar to the final exam, and then a post-test. That would be an example of dependent sampling. Each student in this class would provide me with a pre-test score and a post-test score. That's dependent sampling. Independent sampling would be a situation where we have two separate classes, maybe one being taught online and one being taught in seat. And I get the final exam score from each of those classes. Some other examples of dependent samples would be pre and post test that I just mentioned. Studies involving husbands and wives. Since there's a connection between the husbands and the wives, that would be dependent sampling. If you just had men and women in two samples, those would be independent samples because there would be no relationship between the two samples. Some side-by-side product testing is also dependent sampling. This would be example of this would be if you had to rate two products, and so you would rate the two products, maybe two different colas, on a scale of 1 to 10, and then the next person would rate them, but each person would rate both of the products. And so the data would come from a single set of people, I guess. Each person would give two numbers. There's another way to get dependent sampling, and that is done by what's called matched pairs sampling. What matched pairs sampling is when you have two unrelated sets or sources used, but the subjects are matched up according to some third variable, one set from each population. So what you could do is if you were comparing people who were trying to lose weight, maybe dieters and exercisers, and you have a group of people who are dieting and a group of people who are exercising, you could match them up according to their initial weight, so that you put the two people who are 250 pounds, match them up, and you match up a pair of people who weigh 150 pounds. The reason you would do this is because the 250-pound people have a lot more weight to lose, and theoretically they just have more weight that they could lose than the people who weigh 150 pounds. So what that does is it removes that wall between those two samples and it connects them. It makes a connection between the two samples. So some examples, students might be matched by IQ. So if we were comparing an online class with an in-seat class, we might want to match the students up according to their ability level, so that two students with IQs of 110 are compared with one another, and two students with IQs of 130 are compared with one another. That way you're comparing apples to apples and oranges to oranges. Anyway, dieters might be matched by initial weight data, but we won't pair the people up. We will do the non-paired test. The two-sample t-test that's non-paired, if you remember, this is exactly what we've done earlier this week. We start with the parameters, and the first parameter is the average weight loss for dieters. Second parameter, mu2, is the average weight loss for exercisers. The hypotheses are, null hypothesis is that the two averages are equal, and the alternative hypothesis is that the two averages are not. The distribution we're using is T. Specifically, it's the T sub 6 distribution, because there are 2 samples and a total of 8 people. At any rate, I punched this into my calculator. I won't go into the details because you know how to do this, or you can watch the technology video. And my answer was a p-value of 0.1074, which means that there is not evidence to suggest that a difference exists in the average weight loss for dieters and the average weight loss for exercisers. Now let's compare this. Well, okay, except the null hypothesis. We're going to compare this with the what happens if we pair this data. So that what we just did was a non-paired t-test. Let's pair it up using a dependent sampling technique. When you do this, our hypotheses are going to be based on the differences between the pairs of data. So we're interested in the differences between the pairs of data. And we're going to test whether the average difference, that's mu sub d, is the average difference, is equal to 0, or less than or equal to 0, or greater than or equal to 0. So number 1, parameters. Earlier we had those 2 parameters, but we're not interested in those anymore. We're interested in the average difference between the weight loss for exercisers and the weight loss for dieters. Something to note is that the average difference between the weight loss for exercisers and weight loss for dieters is not the same thing as the difference between the 2 averages. And to emphasize this, hypotheses. We're interested in if that average difference is equal to 0 or not equal to 0. The distribution is the t-distribution. Specifically, it's actually the T3 distribution, if you want to do the subscript thing. 3 degrees of freedom, because there are actually 4 differences that we're going to compute. I'll show you the differences on this next slide. So you see the 4 differences. You have the pair of dieter exercisers who started out weighing 250 pounds and their weight loss. The difference was 10 pounds. You have the pair that started out at 175, and their difference is 10 pounds. And I have to be very specific here that I'm doing the difference between the second number minus the first number. So be consistent. Always try to do it a certain way. Just pick which way you're going to do it, because the way that you do this, the way you do your difference, will affect your hypotheses and so forth. So I'm doing exerciser minus dieter. At any rate, we get down to the bottom here, and I've got all my differences, and essentially I'm just going to do a 1 sample t-test on those differences. So it's just these differences here that I care about. My p-value is 0.01592. Now you're wondering, how in the world did he get that? Well, I did a single sample t-test. This is just the t-test. That's the second thing on your calculator when you go over to stats tests. If you want to actually see this done, go to the technology videos for this week and check the dependent sample t-test, and you'll see a similar problem done. Anyway, step 5, we're rejecting the null hypothesis, and there is evidence to suggest that the average weight loss due to dieting is different from the average weight loss due to exercising. Let's do another example. A composition teacher wants to know whether a new grammar program will reduce the number of grammatical errors in her study, or in her students. So she has 6 students write a 2-page essay, then administers the new grammar program, has the same students write another 2-page essay. We're setting alpha at 0.025, and we want to know if we can conclude that the number of errors has been reduced. The first step is to note that we're interested, I guess we need to write down our parameter. And the parameter is going to be the average difference between errors before and errors after. So I'm interested in doing the difference, the before minus after difference. In other words, student 1, I will compute 12 minus 9. That'll be my difference. Now it's important that I note exactly what I'm going to do, because notice that this teacher wants to know whether or not the program will reduce the number of grammatical errors. And so specifying whether we're doing before minus after or after minus before will affect the hypotheses. Since I'm computing before minus after, it means that I'm expecting the differences to be positive, such as with student 1. Student 1 had 12 errors before the program and 9 errors after the program. And so 12 minus 9 is 3. And so since I'm anticipating the errors before minus errors after to be positive, my alternative hypothesis is that the average difference will be positive, greater than 0. If you were to do the opposite, that is, compute after minus before, then you would expect the numbers to be negative, in which case your hypotheses will look different, but when you get to the conclusion, you would have the same conclusion as I have. So one of the irritating things about this test is that you could do it one of two ways. You just have to keep track of exactly how you're doing your calculations. At any rate, that's my hypotheses are there, and I've got my data. So the next step is to actually compute those differences. So I've got those differences here. Notice that student 1 had a difference of 3, student 2 had a difference of 3, student 3 had a difference of -1. He committed one more error after than he committed before. And then the rest of the students you can see there. So I've got my differences. All that's left now is to do a simple t-test. That's just the one sample t-test with those differences. So those differences are what matters. We're going to type them into our calculator. So on our calculator, I've typed in the differences into list 1. If you watch the technology video for this particular hypothesis test, you can see another way to do this by typing in the two lists of numbers and then doing the difference on the calculator. But all I need are these differences. And so they're in list 1. Then I end up with going over to tests, and notice just the basic t-test is the one I'm selecting. I select the input method is data. Mu sub 0 was 0. List that I'm interested in is list 1. And the frequency is 1. And then my null hypothesis, my alternative hypothesis is mu is greater than 0, or mu 0. And I clicked calculate, and I got this as my output. The p-value was 0.0377, which means that there is evidence to suggest that the average difference between before and after scores, before the grammar program and after, is greater than 0. In other words, there is evidence to suggest that the grammar program improved the scores. So that's it. Don't forget to check the technology video for this to see how to how to do this on your calculator.